thanks to the organizers for having me here. It may have something to do with the fact that one of them is a co-author on the paper behind this talk that just demonstrates the slightly incestuous nature of our community. So I'm going to talk about concrete compositional sentence spaces. This is sort of a follow-up from some of the talks we've had on the overlap between category theory and linguistics earlier in this workshop. So on Friday, Stephen Clark talked a bit about lexical semantics as an interesting way of obtaining a representation of word meaning by saying that they're vectors, and obtaining vectors from their corpus by looking at the distribution of how words occur within a context. And that this was quite successful in doing things like source extraction. And briefly talked about how categorical methods could be used to integrate syntactic analysis into composition operations for these distributions. On Saturday, Bob Coecke talked a bit more about the relation between category theory and modeling information flow, showing that the way in which we model information flow in physics is actually not that different from the way we can model information flow in linguistics using compact closed monoidal categories, and that there's this cool diagram and these yank operations which allow you to simplify how you're going to represent different semantic operations quite well. So that was all very abstract, and what I'm going to talk about today is how you can make it concrete, how you can sort of flesh out this skeleton formalism and obtain something that we can use in linguistics, or a sort of a set of tools we can use in linguistics, and more importantly perhaps that we can evaluate and show that this abstract formalism has some merit from an empirical standpoint. So in the talk today I'm going to briefly go through how this categorical compositional distributional model works on the abstract level and talk a bit about some cool features of it. I won't go into much detail here, so I can focus mostly on how we're going to actually flesh it out, how we're going to find the semantic spaces, how we're going to build the vectors from the corpus, and naturally I'll give you some examples that hopefully will clarify how we're doing things and show you that this way of doing things has some merit. And finally I'll talk a bit about some sort of future work that we're going to do this, especially the need for richer evaluation mechanisms, which currently don't exist. And maybe if we have some extra time, I'll talk a bit about some cool stuff I've been working on this week. So to start with, so the categorical framework that Bob presented briefly and Stephen presented briefly during their talks on Friday and Saturday is interesting because it sort of brings together syntactic analysis into the composition operations. So we have vectors representing the meaning of words, and we want the parse tree or the dependency tree to act as a function upon these word vectors to get a sentence vector. So if you want a take-home motto about how what this framework is doing, it represents how syntactic analysis guides semantic composition. One of the interesting features is that it's abstract, so there's no commitment to a particular way of filling in the vector spaces that we're using for semantic representation. So we saw in the examples that Bob and Stephen and Ranush give in their paper and briefly mentioned in the talk, we're talking about we're projecting sentences into this Boolean space where they're true or false. But there are other ways of doing it. You could have well, we're going to see one in this talk. And it's super abstract because there's actually no particular commitment to which grammatical formalism or algebraic structure you're using for semantic representation. So in Anne Polier's talk in Esley this year, she talked about using vector spaces over lattices instead of just classic vector spaces. You can use the category of relations, and if you want to guess something like quantitative semantics. As long as you can give compact closed monoidal categorical semantics to your models, you can fit them into this framework. So how does it work? Well, briefly what we're doing is we're going to first represent your method of grammatical analysis, so we're using pre-group grammars in our actual applications as a category key, and so the objects are going to be the types, so we talked about this briefly during Stephen's talk. And the actual analysis steps, so reductions in pre-group grammar or left and right applications and CCG are the morphisms of this category. So when you have something in this adjoint that cancel out in the pre-group grammar, that's going to be one of the morphisms of cup, the diagrammatic calculus. And on the other hand, we represent the word semantics as another structure in another category F. So we're going to be using vector spaces. So we're going to have a category F vector spaces. And the morphisms of this category are going to simply be semantic composition operations. So if we're using vectors, they're going to be later maps in the form of inner products. And finally, how we bring them together is we have a product category P cross F, which brings together the morphism used for grammatical analysis, which then dictate which sort of composition morphisms we're using to project into sentence space. So we'll go through that in a bit more detail when we move through examples. The attractive aspects of this framework, I think, are it's conceptually close to Montague semantics, which is earlier work in the 70s of relating syntactic rules to semantic interpretation. Maybe that could be viewed as slightly ad hoc because, in fact, in this framework, one of the interesting features is you really do have this sort of like systematic method of going from syntactic analysis to semantic composition. So that's an interesting feature. It's highly modular, as I said. We have a lot of liberty as to how we're going to be filling out the spaces, and we're going to be exploring at least one of those today. And finally, as we've been exploring through this workshop, one of the big themes is that as this intuitive connection through category theory to how quantum information flow works in physics. And finally, it has this elegant graphical calculus for representing operations in this formalism. We're not going to focus on that too much within this talk, but Bob gave you a pretty good overview of that in his on Saturday. So what's missing to make this concrete? Well, obviously, you need a way of filling the semantic spaces. You want one of the big attractions of distributional models in lexical semantics is that the language really does sort itself out to give you these word meanings. You just give it a corpus, and then you can calculate the meaning of all these words automatically. And we want a way of doing this. So to specify how we're going to do this, I guess the first question you have to ask yourself is, what sort of semantic representation are you looking for? What sort of semantic similarity is at play within the application areas of your model? And then I'll go from that, showing how you can actually define the semantic spaces and then construct them from a corpus. So what sort of semantic similarities could we have? Semantic notions underlying or semantic representation. It could be truth-theoretic. So we could be representing sentences, as Bob suggested in his talk, as vectors in this space that just is true or false. And that's quite interesting because we have, rich existing logical tools that we can use to reason about, various things and have inference. But it's problematic, I think, from the distributional side because it's not immediately obvious how you can read truth from a corpus. And in the sort of examples that were examined in the Coecke and Sadrzadeh and Clark paper, you sort of specify the vectors model theoretically, where you have vectors over individuals like Bob and Stephen and Ranush, and you have vectors over drinks like beer and all that, and then the vector for likes basically tells you it's true if Bob likes beer. But we have something else. So what else do we have other than truth? I mean, truth is just one way of analyzing language, and there are other ways of, I suppose, conceiving of the analysis of language meaning. And if you don't agree with that, here's a little thought experiment to pump your intuition. So let's imagine we have these three sentences which are all true. So Bob likes cold beer, Bob dislikes warm beer, and the quick dog hunts the red fox. Now, if they're all true, and all we're doing when we're representing sentence vectors is projecting them into a meaning space where they're true or false, then there's actually no way of distinguishing or grouping these. But if I was just to ask a man on the street, well, can you just group two sentences that are more similar here? I think intuitively, Bob likes cold beer and Bob dislikes warm beer would be grouped together, not simply because the terms Bob and beer pop up in them, but just because they're talking about the same sort of state of affairs or state of the world. And it's not just a matter of their truth, it's a matter of their, I suppose, interconnectedness of meaning. And we really want to specify sort of semantic representation that allows you to do this sort of grouping. Well, this is one of the ways we're going to do this. So how do we do that? We're going to rely on this bundle theoretic notion of semantics. So bundle theory is a philosophical term, and you don't really have to worry too much about that. It comes from Hume's work on identity. But the basic idea is that objects of the world are just identified by collections of properties. So two things have the identical collection of properties that are the same thing. Well, the objects in our discourse are just nouns. So dogs, cats, Bob, beer. And other syntactic types either act as modifiers or as filters, or they combine these properties. So for example, an adjective modifies the properties of the noun it's applied to form a noun phrase. And verbs will sort of interlink properties to form sentences. And the diagrammatic representation we've been seeing quite a lot this weekend sort of, I think, visually supports this intuition, where you can see that sort of the information from Bob flows into the verb likes and is mixed with the information from beer that flows through the modifier cold, and then out comes the sentence. So that's kind of a cool idea. But you're probably thinking, what's this guy talking about philosophy and properties and these sort of abstract notions when we're trying to do sort of like concrete implementation. Well, obviously, we need a practical definition of what properties are in order to be able to construct something with it. So I make the claim here that we're already using this notion of properties in standard distributional models of semantics, like the standard lexical semantics we talked about with vectors during Stephen's talk. In the standard models, the class of properties is occurring within the same context. So to give you a short example that you might have found in one of the earlier talks, you're building the vector for dog, and let's see, we see in the corpus that the word bark occurs 10 times within the context of, say, a 10-word frame of the word dog. So the relevant property here is bark occurring in the same context, which we're just going to call bark. And we associated that with one of the basis vectors of our noun space. So that's what we're already doing in standard distributional semantic models. What I want to do in this sort of instantiation of the model is have a slightly richer notion of property. So I suppose that typically linguistically we view properties as being attributes or predicates. So for example, we say that dogs are typically fluffy, or they typically bark a lot, or suppose students are typically drunk or typically studious, things like that. But how can we represent this sort of like typical notion? And the proposal I'm putting forward is to annotate the basis vectors of our noun space with dependency relations paired with lexicon terms. So these are going to be our properties, these dependency word pairs. And I'll give a little example to explain how that works. So we're building the vector for dog, and we're going to count, for example, how many times dog is the argument of the adjective fluffy. So we're calling this property simply arg fluffy, where arg is the dependency relation and fluffy is the word. And we annotate one of the basis vectors of our noun space with arg fluffy.
So do the basis vectors range over all pairs then?
Yeah. It's a big vector space. But obviously there's, well, I can talk a bit more about the optimizations you can do, but it's going to be sparse vectors. Computation to represent everything. Then we count how many times dog is the subject of run, call this subject run, how many times is the object of pet, etc. Object of petted, or patted, and so on for all dependency relation word pairs. So there's a few questions with this sort of like definition of properties. Well, we've just sort of seen how we're going to deal with nouns, but how do we represent the fact that verbs relate properties, or that adjectives modify properties of nouns? Also, what's the semantic structure of other grammatical types in what we with view? How do we conceive of what an adverb is doing, or indirect objects? And finally, what's the structure of the sentence space itself that we're going to finally project all the sentences into, so that we can compare sentences with different syntactic structures. I mean, if you have any expertise in the field, one of the big problems with some of the other approaches to compositionality and distributional semantic models is that either you lose a lot of information by throwing everything into the same space, or you add structure by using tensors, like Smolinski did, but then sentences of different length and different grammatical structures that can't be directly compared with the inner product, and we really want that. So it would be convenient, I think, to answer these questions, if all these larger spaces were built upon this noun space, this property space that we just defined. And I'm going to show you how we do that. So the formalism we're using gives us a way of defining semantic spaces from grammatical types, such that the structure of a grammatical analysis formalism kind of generates the structure of a semantic representation formalism. So the way we're doing it is when we have a type A in our pre-group grammar, which is also going to be an object in our grammatical category, we assign that to a vector space, capital A. So this is just going to be the pair, the small a, capital A is going to be a pair in our product category, P cross F. So for noun and noun adjoints, we're assigning the same property space N. And so on for transitive verbs that are actually they're not non-atomic types, so a transitive verb is going to be of pre-group type NR, S, and L, so it's something that expects a noun on the left and a noun on the right and uploads a sentence. We assign the space N tensor S tensor N. And for adjectives, we assign the space N tensor N because the pre-group type is N and L, and so on for other types. So we can do that systematically because of the categorical formalism we're using. Well, what's left is, so if we look at what we did for transitive verbs, there's this S floating about in there. And one of the things is we wanted to build everything up from noun space, which we can because, but we need to sort of specify what the S is going to be, what the sentence space is going to be. So this is a point of debate: is do we want to have that sort of naturally emerge from the model, or do we want it to be something that we can just stipulate? In the way we're doing things here, we're actually just going to say, well, here's what our sentence space is going to be. And it seems ad hoc, but if we have time at the end, I'm going to talk about how we can actually define S to be other things for different, I suppose, different natural language tasks. And we don't have to change anything else in how we're doing things in the model. So for now, we're going to stipulate sentence space to just be the tensor space of our property space. So the basis vectors of S are going to have the shape Sj equals Ni and k, so a pair of basis vectors from our noun space. And this might seem a little ad hoc, but I'm going to show you how this sort of fits the bill for our task of comparing sentences later. So now we need to move on to how we're going to actually construct these semantic spaces from the corpus, how we're going to fill them with vectors. They're obviously already filled if you're considering we need mathematical spaces, but we need to actually build them computationally, right? So for nouns, I mean, we already kind of went through it. It's very close to how you build noun vectors or any sort of vector in standard distributional semantic models. So you're counting the number of times that the target word, let's say dog, has a dependency relation, let's say arg, with the word fluffy in our corpus. So we assign this count to the weighting ci associated with ni, a basis of the noun space, annotated with arg fluffy. And finally, we do this for every such dependency relation and word pairs such that we can represent the vector as a superposition of the weighted pairs, the weighted bases of the noun space. So that's pretty standard. So vectors are where it starts, verb vectors are where it starts to get a bit more complicated. They live in a larger space, and there's this sentence space that's embedded within verb space. So we need to sort of have a slightly more clever definition. So I'm going to define this mathcal C to be a structure representing corpus words and dependency relations. So let's say the B and C is going to be one such structure. If you want to think about concretely what sort of structure this is going to be, you could just imagine that every sentence is going to be a dependency tree, so that you can just read dependency relations and words from the tree. And so C is basically going to be a set of dependency trees. And we define two functions, subject of and object of, over this structure, such that if you pass a verb token, the subject of is going to return its subject. So noun, it'll return a noun. Or the empty string if there is no subject. And if you pass a verb token to the object of function, it's going to return its object. And if there is none, such as in the case of intransitive verbs, then it's going to return the empty string. This empty string is not just something that we're throwing in here for no reason. It's actually going to have a pretty important role when we're going to be talking about how to construct intransitive verbs. And so each vector V in our verb space is just, once again, it's a superposition of the weighted bases. So Cij, is a real number, it's going to be a weight, and then Ni, Sj, and K is just the basis of verb space. And so all that we really need to do to get a verb vector is calculate all these Cij, K weights. So C is basically just going to be a three-dimensional matrix. And we express each Cij, K weight for verb V as the following expression, so it's a bit complex, and I'm going to walk you through. So Cij, K is simply equal to 0 if Sj, which is the sentence space basis, doesn't expand to Ni and K. What does this mean? We're basically saying that we're going to disregard every case where it doesn't give us, where the counts Cij, K won't give us any information about how two properties are interrelated in the word. We're only looking at the cases where the properties of the objects and the property of the object and the property of the subject are interrelated into this middle pair, Sj. And then let's walk through the rest of this. Then you have this MC value here, which is simply a weighting so that we're ignoring all the verbs that aren't the target verb. So since we're actually summing across all the verbs in the corpus, we want to ignore all the ones that aren't the one we're constructing the vector for. And finally, these inner products are taking the object of the subject of the verb and seeing how much it has the property Ni, and take the object of the verb and see how much is the property Nk. So if you want to read what this expression is saying, is we're basically going through the corpus, and counting for each occurrence of a verb, let's say runs, how many times it relates one property to another. And that gives us, each CIJK weight is basically standing for how many times the property NI is related to the property NK by the subject and object of that verb. So this might seem very transitive verb-centric, and I argue here that you can actually easily extend this vector construction method to deal with intransitive verbs, and indeed also to verbs that have both a transitive and an intransitive form, like most transitive verbs do. So let the vector for this empty string simply be the superposition of the basis of the noun space. So this means that trivially, the inner product of the epsilon vector with any basis nk of noun space is always going to be 1. So for intransitive verbs, we're just simply not going to change anything to the previous equation, because object of VC for an intransitive verb is going to return the empty string, and the equation will sort itself out. Where here you had object of VC, the inner product of object of VC with nk, that's going to be 1, so it just cancels itself out, and you obtain this expression right here, which is pretty similar to the previous one. And the semantic rule of the operation of taking the inner product of epsilon with nk is semantically to cancel out the contribution of the object to the verb's representation. So in the case of intransitive verbs, or transitive verbs that occur intransitively within the corpus, the verb is solely characterized by the properties of its subject. Yes. And adjectives, we'll go through it. It's actually quite simple. It's very close to how we deal with verbs. So you have a function argov, which returns the argument of an adjective token in the corpus. We take the Cij weights much in the same way. We ignore every case where the adjective token is not the adjective token we're building the vector for. We ignore all the cases where ni and nj are the same vector, because we want to sort of, it flows through the adjective. So we want it to just modify this one property at a time. And we take the inner product of the argument of AC with the basis ni. So what we're doing here is we're just basically viewing the adjective as being characterized by the properties that its argument typically hold in the corpus. Is that fairly clear? So let's make this a bit more approachable by looking at some examples and seeing that it works. So obviously, the whole point behind doing this is that we can then just feed into corpus like the BNC dependency tag it, and get the vectors for everything we need, and then just go about starting to build sentence vectors and compare them. Obviously, that's a non-trivial task from a programming standpoint, and also it would be pretty hard to present those results with nice tables. So what I did here was I hand-constructed distribution for nouns and verbs for the sake of the examples, and I hope you'll believe me that you get good results. Well, you'll find out that you get good results for actually using the BNC. You'd have something quite similar, I think. So here we see that we simply have the words as the top row, and then these are the properties. So we notice that bankers aren't very fluffy. They're quite ferocious, and they're fairly shrewd. And that kittens are fluffy. I don't know why kittens are fluffier than dogs, but we'll ignore that. And they're slightly shrewd. Cats are a lot fluffier and shrewder than dogs, but not as shrewd as bankers.
You're saying that bankers can't be bought?
I didn't want to get political in this one. Yeah. Oh, okay. Well, we can obviously in a real news corpus there might be a few more weights there.
Not in the same way as dogs and cats.
Not in the same way. Well,
that's true.
Anyway, and we're also going to handcraft these Cij-K count matrices for a few verbs. So you'll notice here that Cij-K matrices should be 3-dimensional matrices, and here what I presented are 2-dimensional matrices. Well, why is this? We can actually simplify the matrices into 2-dimensional matrices by ignoring all the cases where there's a natural zero. This is where the cases where ni and nk are not equal to sj. Well, where the pair ni and k is not equal to sj. So this is kind of like a diagonal slice of the matrix, of the 3-dimensional matrix. And you can do this sort of dimensionality reduction trick for adjectives and adverbs as well. So here we sort of we read that something ferocious chases something fluffy 7 times in the corpus. That something Right? This is sell something valuable is sold by something shrewd 8 times. So this is, it's hand constructed, but it was intended to sound fairly plausible. And I would like to specify that I didn't, when I did the initial evaluation, I did just like build these by hand and then go forth and do the calculations with the results of which I'll present. So there wasn't, I didn't go back and tune it, but you have to just trust me on that. Obviously, when we're getting onto some real serious evaluations, so this won't matter that much anymore. And for our examples, we're going to use the similarity measure. The similarity measures we're using for our examples is the cosine measure. So that, if you're not familiar, but I'm pretty sure everyone here knows it, it's just, you know, you're normalizing the product of 2 vectors by the product of their length. And we're going to compare the semantic similarity of 3 pairs of sentences. So dogs chase cats and dogs pursue kittens. So these are, you'd expect them to be fairly similar because kittens are very close to cats and pursuing is quasi-synonymous to chase. Dogs chase cats and cats chase dogs. Well, you know, if we weren't caring about word order and syntactic structure, if we were just adding vectors to get sentence vectors, these would be identical. But here, even though the words are the same, we're going to show that the word order actually will change the results, as you'd expect. And finally, we're going to compare dogs chase cats, and bankers sell stock. And these are both, from the tables we've seen in this corpus, they're both equally plausible. Like bankers often sell stock in the corpus because they're shrewd and they're ferocious, and stock is valuable. And likewise, dogs chase cats because cats are furry and weak, and dogs are hungry and whatever. So yeah, so the first pair is intuitively quite similar in meaning, second pair is lexically similar but syntactically different, and the third pair is equally plausible, but we expect them to be semantically different, obviously. Just like in our first example, Bob drinks beer and the red fox is chased by the brown dog, something like that. So I'm not actually going to go through the math in detail here, but the comparison of dog chase cats and dogs pursue kittens is simply taking the inner product of the superposition of the weighted, superposition of the weighted of the weights for the verb, and then the inner products are something you get from the morphisms and the categories. So that I'm not going to go through how the composition operation works in detail, but you can read that in the paper. But the whole point is that, you know, you plug it into the sort of like standard calculation that we would do in any instance of this formalism, and the cosine value is 0.97, so you can read that as 97.9 semantic similarity for these, which is quite high, but then we are using really simple noun vectors, so there's not much to differentiate cats and kittens, or indeed chasing and pursuing. So we get the result we kind of expected, high semantic similarity. Okay, dogs chase cats and cats chase dogs. The word vectors for dogs, chase, and cats are the same in both sentences, but the sentence structure is different. And we obtain here a cosine value of 0.656. So that's still quite high, but once again, it's because we're using a fairly simple model, and there's not that much to distinguish dogs and cats. But we do notice that just, you know, changing the syntactic structure will give you a huge drop in similarity. So that's the result we were kind of hoping for. What would happen if we just, you know, had something else like, you know, cats, dogs chase? Well, if we're still seeing those things as nouns and then a transitive verb, then it's not going to be a correct form, so it won't actually project into the sentence space at all. And finally, dogs chase cats and bankers sell stock. Well, they're both quite plausible, but the cosine measure value we get from the data I had provided previously gives us a 0.042, so 4% similarity. And once again, this is kind of what we're expecting. You know, they're plausible. They're both, let's say, true from the corpus, if every sentence in the corpus is true. But they are very dissimilar on a semantic level. So that gives us the result we wanted. So, how much time do I have left? 5 minutes? Okay, so I'm going to briefly talk about how we deal with other syntactic classes. They're all actually very similar. So adjectives are N and L, so they live in this space N tensor N. Well, I talked about how we deal with adjectives actually. Determiners are actually just adjectives, but since determiners are a closed class, we can actually, for determiners and other logical kind of words, we can just specify what the vectors are by hand. And in fact, this is if there's any sort of logic in this sort of higher order logic in the system, this is where this is how we do it, is by specifying what the weights are for determiners. So for example, a word like the, I'm just going to say the weights, the C matrix for the is just going to be the identity matrix, because I wouldn't consider it to change anything. Indirect objects, we haven't really figured out how to collect the counts, but once again, it's just collecting CIJ counts. And adverbs, we have figured out how to do this, and it's still just doing CIJ counts. So there's something that, you know, collect the counts for an adverb, you're just looking at the properties that the verb it modifies typically interlink in the corpus. So let's look at quickly look at some more complex evaluations. If you take some handwritten simplified, so we did the same sort of like dimensional simplification here, like taking out just taking the diagonal of a two-dimensional matrix. You get these line matrices for fluffy, shrewd, and valuable. So we can compute a more complex sentence comparison, like fluffy dogs chase the fluffy cats, and the shrewd bankers sell valuable stock, and see that we still get the sort of result we want, so 0 point. So that's 1% similarity. And transitive versus intransitive verbs, well, it's quite simple. There's no object for the intransitive verb. The CIJK matrices are calculated as I specified earlier in the talk, so it just works out like you'd expect it to. So dogs chase cats and dogs chase have a similarity of 0.961, so you get this intuitive result that dogs chase is a generalization of dogs chasing cats, a more general thing. So therefore it's similar but not completely identical. So this is great because a lot of other models, as I said earlier, a different syntactic structure would mean that you wouldn't be able to compare them directly. But here, since you're projecting all sentences into a common space, then we can directly compare them without problem. So we get the results. To summarize it, sentences that are similar in meaning obtain high similarity scores in this model. Sentences with similar identical terms with different syntactic structure are less similar, and semantically unrelated sentences have low similarity scores. And as a little bonus, these last two lines show that you can compare sentences that have different syntactic structure, and that you can actually do some pretty complex sentence comparisons within this model. So summarize, we showed how to flesh out a formalism that combines syntactic and semantic analysis to allow you to produce sentence vectors from word vectors. We looked at how you can actually fill these vector spaces from a corpus using this more complex notion of properties. And I gave you a procedure for building the model from a corpus. And finally, we looked at these examples.
If you want to keep going, it's just that if you want some questions, we probably just
Okay, well that's about it. So let me just talk just for a minute about evaluation. We're extending the model to cover more semantic types. So the evaluation we're running right now is we're looking at how well this works for noun-verb disambiguation tests. There's previous work by Mitchell and Lapada in 2008. We're running the same experiment, and we hope to obtain equivalent or better results. I have a paraphrase corpus, which is an extension of Lapada's paraphrase corpus, which is itself an extension of the Microsoft paraphrase corpus. And we can use paraphrase detection tasks to see how this model works on a larger scale. And finally, we want to see how helpful this is in doing actual NLP tests, like semantic search. So that's what we're going to be working towards over the next 2 years. Thanks for listening.
Any questions?
So when you were building the semantic representations of verbs and adverbs and so on, you're kind of doing it at the vector space level. It seemed to me that it looked like you could give much higher level descriptions of those procedures, in the language of using evaluation maps and so on, in the language of the labeled categories with various bits and pieces, and then it would just map down into those concrete things. And obviously, you might want to check it that it was looking right in a quantitative sense, but I mean there should be some general thing there. And of course, the advantage of that is it has some generality and it might apply to other representations.
No, so obviously, one of the things, because there's so many different syntactic types, if you're using something like, say, CCG instead of pre-groups, there's going to be there's like 200 common CCG types, so that means they're going to have quite a lot of vector spaces where you're going to have to give a semantic representation, and effectively you'll have to systematize it. So I completely agree that this is something we're going to be looking into, and how to sort of like go from the abstract down to the concrete, and indeed check that it works. For now, we're sort of like, my first priority personally is to get an evaluation of this, what we've got so far, is to justify future work and hopefully get some more funding for this, some more people interested in working on this project. But that's eventually what we're working towards.
Is there a question?
Yeah, I was going to ask,
I mean, we obtain it from the syntactic analysis, right? So it's not. I'm not quite sure I understand the ad hocness in there.
You're talking about the verb as a...
No, you say noun can be in, so it can be a
set of properties or something.
properties, yeah.
So is that ad hoc, you ask?
Yeah.
Oh yeah, so it's a particular choice that we have for like, when we select what the basis of our noun space are, and this seems to be an intuitive way of doing it. But there's no commitment to doing it specifically in this way, as long as you're using the same sort of count mechanism, you could probably solve it.
It's not ad hoc because it's followed on the set. In the structure, but
All right, one last question.
it's in the family.
Yes, could you maybe show again your comparison of results for the sentences? About 3, 4, that one, yes.
Those are small.
If I look, you seem to be comparing two things at the same time. First the context, and then the truth, because dogs chase cats and cats chase dogs, as far as I can see. The context, just the neighborhood birds, is the same. Of course the order is not the same. And that's just what we find, because we find it more or less likely that cats chase dogs and the other way around. Is that what is reflected, or is just...
No, it's not. It's not. It's
because we use it that way.
It's just because chasing. I'd say that the verb chasing is characterized by what does the chasing and what's being chased, what sort of properties they have. And so cats might chase mice. That might get.
You have to have a prior knowledge of the world to understand.
No, you can get it from the corpus. I mean, this is the whole construction procedure.
Okay, so everything in the corpus is true, and then you get your...
Yeah, so they're mostly plausible. But so I mean, there's two things about like by going second order, by looking at properties rather than at tokens. You know, someone said, well, listen, if a news corpus is more likely to have a lot of occurrences of man bites dog rather than dog bites man, that doesn't matter for this, because as long as you have regular occurrences of dog in other sentences, as dogs biting cats and other things like that, and regular occurrences of bite, like something aggressive biting something weak, and regular occurrences of man, so like you can collect the properties. It doesn't matter that the sentence, you know, dog bites man never shows up in your corpus. You can still get a semantic representation that's somewhat plausible. The second question is there any sort of notion of truth? Well, if there was, then dogs chase cats, which is, you know, plausible. Let's say it occurs a lot in the corpus, and banker sells stock, which is very plausible in the corpus, would be very similar. But no, here it's because there's different properties being related by the verbs, and there's basically a different sort of meaning underlying it. You obtain the desired effect of having a low degree of similarity.
You know, I was a bit puzzled by the notion of plausibility, because that would be my question, because it's not clear how that comes out in the framework at all. I mean, it might do in the sense that when you get your counts, of course, you get it from a corpus, so the counts naturally reflect reality, which doesn't answer your question. So that reflects what's plausible.
Yeah.
But it's not obvious how that would flesh out in the similarity comparisons. So if you take a plausible thing with a non-plausible thing, whether that would affect the degrees of similarity, that's not obvious to me.
Well, I mean, just from the sort of mathematics, if you had dogs chase cats and something like, you know, bankers bite kittens, you'd have that bankers bite kittens would have a lot of zero or very low value basis weights. So I mean, that would basically give you a low degree of similarity with almost everything, except itself.
Maybe that's a problem with using the case line similarity.
Okay, let's stop there. Thank you.
Okay, so the remainder of the time we have scheduled a panel session, and since I'm the only one who had any warning of this, I've managed to prepare some slides. Samson and Bart, wherever he is, would you like to come up and be my friend?
Let's see your slides first.
Yes. I'll show you mine if you'll show me yours. So I started out with just a couple of random sort of observations that occurred to me while I've been listening to the talks. And one is the notion of distribution that's come up. And there are actually two distinct notions in the linguistics literature. And the notion that Ed had is kind of halfway between the two. So there's the notion associated with Zelig Harris, who was Chomsky's teacher, which is this, that you think you're a field linguist trying to figure out the syntax of a language that you don't understand, and you have a big corpus of examples, and in this corpus you notice that you not only do you find ABC, but you also find ADC in that corpus, and more generally observing that some sequence within a larger sequence can be replaced by something else suggests that they have the same distribution, as it were, so they're similar in some ways. So for example, Bob drinks beer on Fridays is a sentence in our corpus. Bob sleeps on Fridays is a sentence in our corpus, so that tells us that sleeps can replace drinks beer, and putatively therefore is the same kind of unit. We also notice that just Bob sleeps is in our corpus, so sleeps can be taken to replace sleeps on Fridays or drinks beer on Fridays, so that's a unit of the same kind. And that notion of distribution is meant to be more or less independent of meaning, in the sense that all you need is for the sequence to be in the language. It might not make sense, but people will still assent to it being a possible sentence of the language. So that's one notion of distribution. The other one mentioned by Steve in his talk on Friday is the one that's associated with Firth, what he calls actual words in habitual company. And his idea was that some aspects of the meaning of a word can be partly determined by seeing what it co-occurs with, and an example that he gives is a very British one somehow. One of the meanings of ass is its habitual collocation with an immediately preceding "you silly." Okay, so it's not the normal meaning of ass, but it's the one that is used to indicate that somebody's stupid. And that's quite independent of compositionality. In a sense, the Harris notion of distribution is the foundation for compositionality. It's what gives you the compositional structure of sentences, the syntactic compositional structure of sentences, and as has been said several times, that the semantics follow syntax in this way. Whereas the Firthian notion doesn't necessarily. So, for example, one of the words that collocates very, very frequently with the word work is hard, either as an adjective or as an adverb. So we get work hard, hard work. Now, those phrases do combine compositionally, but other examples, so doctor and nurse, have very high collocations in a corpus, but they very seldom occur maybe in a conjunction like doctors and nurses, but you don't get them in those kinds of structures. So they're two distinct notions, and the distribution, so-called distributional semantics literature has almost exclusively used this notion, and the reason for that is simply because it's easier. You know, you get more observations in a corpus of things occurring in a particular context, but correspondingly you'll get stuff that isn't necessarily guaranteed to say anything sensibly compositional about meanings. Okay, so that's one random observation. The second one is that we're looking for ways of combining vectors which we're getting from collocations at the moment, or moving a bit more towards the Harris notion, the sort of stuff that Ed was talking about, where we take grammatical relationships into account. But the kinds of compositional operations that we may need, I think, are not necessarily going to be just one-to-one with the syntax. So, for example, Ed was talking about adjective-noun correlations. In fact, although the syntax of adjective-noun modification is fairly straightforward, the semantic consequences can be quite various, depending on the semantic property of the adjective involved. So, if we have something like this, Jan is a Dutch logician, that's Dutch is a so-called intersective adjective, so you can infer from that both that Jan is Dutch and Jan is a logician. And in that case, the semantic operation in terms of denotation is you take the set of Dutch things, you take the set of logicians, and you take the intersection. But relational adjectives like short don't behave the same way. So Jan is a short basketball player, doesn't imply, it implies that he's a basketball player, all right, but it doesn't imply that he's short, because even short basketball players are typically over 6 feet. So no, adjectives like this are always parameterized by a particular property. You can't isolate the set of short things, okay, because they'll actually turn out to be the set of tall things as well by some different measure. You might think, well, at least in both of these cases, whatever the noun property is implied, but there are adjectives that don't have that property either. So Jan is a lapsed Catholic. It doesn't even imply that he's a Catholic. In fact, for some people it implies that he's not a Catholic, although I don't think that's true. But certainly there are other adjectives that do behave like that. So a fake diamond certainly isn't a diamond, and a plastic gun isn't a gun. And it's quite difficult to see how counting vectors is going to give us those semantic properties, because pretty clearly if you have got a big enough corpus to get some non-trivial number of observations of phrases like Dutch logician, although in fact looking at most proceedings of linguistics conferences would give you quite a few observations of those. It's pretty clear that the set of contexts in which Dutch logician occurs is going to be a subset of the set in which Dutch logician occurs, and the same is true for all of these. So the relationship between the counts and therefore the vectors is going to be the same for all three, but the semantic properties are quite different. Okay, that's another. Ed mentioned it's good to test, and I don't know whether it's deliberate, but all the examples of sentence similarity that people have given have been of sentences that are structurally isomorphic. So, you know, dogs chase cats, blah, blah, blah. I mean, in fact, a real test is to find something that isn't structurally isomorphic. So, if we can show that a noun phrase like a vegetarian comes out as very similar semantically to someone who doesn't eat meat, then I'd be very impressed. I would be less impressed if it also came out that carnivore was very similar to someone who does not eat meat, even though eating and meat and carnivore are very similar. So getting the logical words right is going to be interesting. Also, I think another test would be, can you capture similarity between relations with these examples that you often get in so-called intelligence tests. So the relationship between finger and hand is the same as, or very similar to that between toe and foot. It would be nice to be able to determine that. Whereas finger is to hand as cat is to mouse. Oh, it's weird. So that would be a good similaritic relation. That would be a bad example of similaritic relations. So those are very challenging tests. That's all I have to say. I think Bart or Samson would like to make some points.
I could say one or two things. Not as specific as this about the, I mean, just from a wider perspective in terms of, I mean, because this is, the interesting point is this meeting is bringing a diverse collection of people together. And, I think it's been very interesting. I'd certainly like to see more of these kind of meetings in the future, more sort of interaction. So one thing that, one sort of general comment that struck me is that so I think even beyond the linguistics, natural language field, I mean, there's a sort of, I mean, one of the exciting things about sort of some of the ideas we're seeing coming forward here is that one looks at the history of particularly artificial intelligence, is that there was a sort of primacy of logical methods in the first 2 or 3 decades, and then a sort of feeling that that hadn't worked so well, and a big move towards statistical methods, which have had successes certainly, but sort of a feeling that the time is right to sort of bring logic and structure back, but to combine it with the strength of the statistical methods. I think what is very nice here is that we're seeing a sort of paradigm for how that could work with a very nice underpinning mathematical structure, which is also interesting to some of the more theoretically minded people. So, and I think that, that one could even imagine involving a wider circle of people with broad interests of that kind, which would sort of further enrich this community. So that was one thought that occurred to me. I mean, one thinks of knowledge representation, machine learning, and wider issues. I mean, some of the work represented in the I guess the other, I mean, you know, thinking in terms of how to motivate work between these communities, I mean, I think there are clearly some very interesting challenges. I mean, the fact that there are these very concrete examples that are mathematically challenging, very concrete ways in which non-commutativity arises, which is always a challenge mathematically. It's kind of, whereas most of the examples in computer science where we've been dealing with canonical categories have been, you know, symmetric, and you can assume things are commutative, and that works pretty well by and large, with some exceptions to do with sort of things that are state sensitive and so on. But I think the very natural and compelling way that non-commutativity arises in natural language is sort of gives a very well motivated challenge to look at these more general settings. So I think that could also serve to motivate people coming from the more theoretical end to be involved in this activity. And anyway, as I say, I would personally hope to see further meetings of this kind, and further interaction, more detailed ones between these communities. That's mostly what I wanted to say.
Yes, well, my impression is that there are roughly 3 communities here: the linguists, the quantum people, and people from the co-algebra community. You see that quantum is sort of in the middle there when it comes to connections to these areas. There are obvious connections we've seen between quantum foundations and linguistics when it comes to information flow, but also which is underpinned by this idea of plugging things in a certain way, resulting in specific flows and manipulations of these flows. Also, there are connections between this quantum world and co-algebra from the perspective of state-based computation and transitions and observations. Although it's still in an early stage, I think that's a fruitful area where things will be happening the next few years. I don't see any immediate connections between linguistics and co-algebra. It's not necessary that there are such connections, but possibly you see certain things. There are, but when you're looking for such connections, it's good to ask the question: is there any state-based manipulation involved? And probably you linguists know better than I do if there is. I can imagine, I mean, the way you analyze syntaxes and you know the way you use such a corpus as a way to interpret sentences. You can see the corpus as a state, but somehow it seems to be a state that is not influenced, not changed by the analysis. You could imagine that you have some sort of feedback that the corpus itself is continuously improving by the further analysis that you carry out. That is a possible approach. But again, I'm an outsider here. Well, what I see of this meeting is that these communities did their best to present their own work and try and present some connections. But I think the real work still has to be done in specific areas, and maybe it's useful for the next meeting to focus a bit more on really trying to elaborate these connections, and not so much a one-way presentation as it was here. Maybe that should be done for the smaller community. My own experience is in getting different communities to work together is that a top-down approach doesn't work, but bottom-up approach may work, but then it's very useful to have a few specific examples that are appealing to several communities, and that you work from these examples and then discuss them jointly. So what does it mean when you say this for this example? And then things become more complete and often more useful. So it might be interesting to try and develop both a set of common examples that people can work on, or even more ambitiously a set of open problems. So if you have feedback on this.
What is an example of a common?
What is an example of a common example? guess this is a question to everyone, and also us to me.
We can walk on to the next one.
I had a comment about your Harris and Firth comparison, which was really interesting. It's not obvious to me that what Ed was doing was Harris necessarily, in the sense that I still think of it as being Firthian, but the way in which you define context is via these dependency relations and so on.
It's certainly not the same as Harris, but it is making sure that things bear some syntactic relationship to each other.
But it struck me that there's another question that comes out of that comparison, which is to what extent you can try and learn the compositionality. So the way it's been presented so far is that we start out with these vectors that are obtained in some way, and then the compositional structure comes entirely through the theoretical framework. But then there's this other question whether you can try and learn some of that compositional structure automatically as well. So that's what you're thinking about a little bit more, isn't it? Actually, what you do is learning the compositional structure a little bit more than an alpha.
So we're learning about such things as verbs and adverbs and so on, and what types they have.
More in the way in which things combine.
Yeah, so
beyond that.
So for example, the kind of problem that Pulman was talking about, where fake gun isn't a gun kind of thing. So how do you learn that automatically from a corpus?
You don't understand this learning thing. People keep using the word learn. What's the word?
Oh, what learning means?
Trying to get something from a corpus.
Yeah, just getting it from data.
Automatically getting it from a corpus.
Yeah, that's all. As in machine learning, it's just a generic term.
You can kind of think of these vectors we've got as learning the meaning in a sense.
Oh, just because they come automatically from the data, that's all. It doesn't mean anything more than that in this context.
Yeah, what I find an interesting challenge is a bit aligned with what Samson was saying, this combination of logic and probability, which I think is really a challenge and underlying what's happening here, and would be useful to have good formal descriptions of what are, I guess, also state-based systems on which you can do observations with certain whose outcome has certain probability, and these as dynamical systems where these probabilities get updated as you continue to work with these kind of systems. And for me, it's a sort of long time question, or maybe I should say in a Buddhist way, a koan. What is a quantum topos? What is something similar to a topos, but involves, in a suitable sense, both this logic, predicates, and probability on these predicates in a suitable mathematical structure.
Yeah, I mean, but what I think I'd just sort of say to add a twist to that is that I think there's been a lot of work in semantics and co-algebra and other approaches on semantics of probabilistic computation or verification of probabilistic programs. But here's a different thing where we're thinking of really of sort of statistical data and using that for inference.
Yeah.
You can get to the whole machine learning paradigm and so on. But it may not be, I mean, maybe some of the tools that we have developed can be used in that direction. I think that has a lot of potential. That's what I was trying to say earlier, because, you know, bringing the two things together, I think is potentially very powerful. We've seen some of that.
Yeah, and what is interesting, at least to me, is this subtle combination of syntax and semantics that's involved. Your semantical, or your knowledge drives your interpretation of the syntax. You had some examples of seeing the man with the telescope, where some background knowledge determines also your syntactical analysis. I think that's also very interesting.
There's another useful distinction to be made, which is that we're talking generally about statistical methods. But actually, when people talk about distributional methods, there isn't really a notion of probability there. It's just this geometrical vector space method. So I think there's another question which maybe we could take ideas from theoretical physics, because my understanding there is that there's a very tight relation between probability and what a vector is in a Hilbert space or something like that. But we haven't really explored that question in computational linguistics. So there's all this statistical work which is somewhat separate from the distributional models that people have been talking about. So it'd be nice to put those together as well.
Maybe the statistical physics actually offers a better paradigm. We really have mass data. I mean, the thing with quantum is that even a single system has probabilities associated with it. But I think
have to be but one.
Yeah.
Or two, was that not?
Yeah, yeah, precisely.
Okay, well I think we've, it's probably time for lunch. Well, I'd like to thank Manoush and Chris for organising, the collaborators for organising this workshop, and for everybody who's spoken and the people who are coming along. It's been really sort of enjoyable and fruitful, if occasionally baffling experience. Thanks very much.